arrive, and everything's normal and fine. Okay, so we've done question 1, and that was worth 8 marks. Okay, this is question 2, and question 2 is this one. Okay, what the idea, by the way, guys, is seriously to finish the paper in as quick a time as we can. What do we mean by electrolysis? Anyone want to tell me what electrolysis is? While we're here, anyone want to tell me? 43. Anyone want to tell me what electrolysis is? Type it in. It's 2 marks. So what do you reckon we should put there? Okay, it's 2 marks. Oh, I've lost you now. What's electrolysis? Decomposition of one compound in a molten aqueous state. Oh, well done, Eric. That's exactly it. Bloody hell. It's better than I would have done. Eric, you're not looking at the answer scheme, are you? But that's a perfect answer. Well done. Okay. Yeah, you've got to mention it's the breakdown of an ionic compound using electricity. Basically, is that. Eric, well done. Excellent answer. All right. Name the type of particles responsible for the conduction of electricity in the metal wires. What's the conductor in the metal wires? In electrolysis? Anyone? While you're doing that, I'm going to copy Eric's. And Eric says it's not chemical decomposition, though, Eric. It's the electrical decomposition. Okay, it's not a chemical process. It's the electrical decomposition of an ionic compound. This is an excellent answer, Eric. Molten or the aqueous state using electricity. Well, I don't have to say electricity because I've already used it, but I'm going to say it. What's the charge carrier in the metal wires of electrolysis? No one? Well done, Ipasang. Well done, Annabelle. It's electrons. And what about in the electrolyte? What is it in the electrolyte? Oh, well done, Ipasang. Well done, everyone. Perfect. Crikey, you're zooming along, aren't you? Right, next. Oh, next one's kind of weird, but let's try and do this. All right. Okay, let's paste this one. There you go. All righty. The table gives information about the products of the electrolysis of 2 electrolytes. Platinum electrodes are used in each case. Okay. Give 2 reasons why we use platinum electrodes. What 2 reasons would you give there? Do it quick, guys. Quick. What's one reason we use platinum? I'm going to answer. If you guys don't, I'm going to get a different color. It is inert. Yeah, I don't think you can say inert because. No, it doesn't say inert, does it? You know what? I thought it said inert, but it doesn't say inert. Well done, Ashika. That's right. You can say inert. Well done. I thought that was in the question, but it's not. Or you can say they're very unreactive. It's the same thing. And as Ashika said, it's a good conductor. Conductor of electricity. There you go. Don't say heat, say electricity. Well done. Excellent. All right, complete the table. All right, we're going to do aqueous potassium chloride. What do we observe at the anode? I think we're going to have to slow down here, by the way, everyone, because if anything, this is when we're going to have to start doing a little bit of teaching. All right, anyone know? Oh, no, you don't observe chloride ions, dear. Yeah, unless you've got a crazy good eyesight, which you don't have, I'm sure. All right, let's do this one. All right. So we've got concentrated aqueous potassium chloride. So we have potassium chloride. What ions are in potassium chloride? You have potassium ions and chloride ions. You've also got the water. What ions does water give? It gives hydrogen ions and hydroxide ions. Okay. Over here, let's have a look here at the anodes. The anode, and over here at the cathode. Anode is positive or negative? Quickly, anyone? Anode, positive or negative? Positive or negative? Well done, Layla. Anode is positive, cathode is negative. Which ions go to the anode in this case? Which ions go to the anode? Yeah, well done. What are the anions? Which ones? Guys, what are the anions? Well done. It's the chloride ion and hydroxide. Well done. Well done. And obviously the cations are my potassium and my hydrogen. Now at the anode, this one, we're answering this one. What ion is going to get discharged? Annabelle is right, well done. What ion is going to get discharged? Oh, it's a nice drink. What ion's going to get discharged? Do we not know? You have a choice of two, chloride or H minus. It is the chloride. Why is it the chloride? Lorata, no dear, we're talking about the anode. Why is it chloride ion? What clue is there in the question? Anyone? Yes, well done, Ketlaho, because it says concentrated. And if it's concentrated, the chloride ion goes. So what's the observation at the anode then? Anyone want to tell me? Don't forget, you can't see chlorine. You can't see it. Okay? So what's the observation? I don't know if it's pale yellow, Eric. Yeah, I'd say a green gas. I would look at this one and I would say bubbles of a green gas. No, Layla. It's a gas, darling, eh? Wait, it doesn't deposit. It coats you'll just see bubbles of a green gas. What's the name of the product at the anode? Well, we know that already, don't we? It's chlorine. So this goes. All right. At the cathode, what ion is discharged? It's one of these two. At the cathode, what ion gets discharged? Anyone? Faya's joined us. Hello, Faya. At the anode, at the cathode, what ion gets discharged? It's either potassium or hydrogen. Guys, we should know which one. Anyone want to tell me which one of these two get discharged? Yeah, why Upersen? Could anyone tell me why it's hydrogen, not potassium? Well done, Annabelle. Lorata, well done. Why though? Yeah, exactly, Upersen. Well done. So the name of the product here is hydrogen. And we know that because it gives bubbles of colourless gas. We knew it was hydrogen. Now we're going to get rid of this rubbish. Oh dear, this is going to take ages. And we're going to do exactly the same for aqueous copper sulfates. All right, and let's see if we can do the same with this one. All right, so we've got copper sulfate and we've got water. What ions are in the copper sulfate? They're copper ions, and we have sulfate ions. In the water, we have hydrogen ions and OH minus ions. Which ones are the anodes? The anode is positive, so the negative ions, these guys, are going to be our anions, the sulfate and the hydroxide. The cations are going to be copper and hydrogen. Okay, so let's say we get bubbles of gas. What gas is that at the anode? Well done, Lena. What is the name of the product at the anode? Well done. It's oxygen, Tissot, and the reason is because the hydroxide ion gets discharged. Sulfate never gets discharged, so this is oxygen. Okay, what gets discharged? Let's do this bit first. What is the name of the product at the cathode? You've got a choice of copper or hydrogen. What gets discharged at the cathode? Anyone? Well done, Yang. Excellent stuff. Copper. Why is it copper? Because it's the lowest in the series. So this one gets discharged. Yeah. All right. And, let me change something here. Let me put this sulfate back. Oh, I made a mess. All right, let's go. So this is sulfate. And this was, what was this? This was OH minus ions. Okay, so what would I see though? What would I see? What observation would I see at the cathode? The cathode is going to get plated. It gets plated because it's a solid going on the cathode. But we can't say it's going to be plated with copper. Okay, you don't know it's copper. What you've got to tell me what you see. And what does plating with copper look like? Does anyone know? Plated. Exactly. Well done, Catalan. Plated with red. It's kind of pink, actually. It's a red brown coat. Exactly. Right. Last question then. Let's do this. Let's do the first one. We had potassium chloride and water, the first one. So we had potassium ions and chloride ions, hydrogen ions and hydroxide ions. The second one, we had copper ions and sulfate ions and hydrogen ions and hydroxide ions. This was number one. All right. What solution is left at the end of the electrolysis in number 1? Can anyone tell me very quickly? What solution is left in number 1? Well, oh, not oxide. Good try. Well done, Annabelle. It's potassium hydroxide. And we can tell that because the hydrogen ions go and the chloride ions go, and we're left with potassium hydroxide. What are we left with in number 2? Let's call this one number 2. What are we left with in number 2? Anyone? Anyone? Number 2. I'm gonna say this is number 2. What are we left with at the end of number 2? Yeah, sulfuric acid. The uranium, you're quite right, but the copper ions go and the hydroxide ions go, and we're left with that, which is hydrogen sulfate. You're quite right, but another word for hydrogen sulfate is sulfuric acid. So congratulations, well done. Okay, now I've got to do some work here. I don't know. This isn't good. I don't know if I've moaned about this before. I'm sure I have, but the thing I'm using, the software I'm using is called Whiteboard, and it used to be so much nicer. They changed it, but they didn't make it better. They made it a lot worse. It's horrible now. You've got, because in the old days I could get rid of everything instantly, but now I've got to do this rubbish. It's awful. It's a pain. Oops, wrong one. Okay, let's do that. Okay, so I think we've done. I think we've done 18 marks. We're doing well, but we've got to rush a bit now. Oh, this looks nice. Get your calculators out, everyone. I'm afraid. Oh gosh, this one looks nasty. This one might take a while. All right, here we go. Let's have a look at this one. We'll do it together. Get your calculators. It's gonna be horrible. All right. So there we are. Tin is a metallic element in group 4. Its main ore is cassiterite, which is an impure form of tin 4 oxide. Tin also occurs in stannite, Cu2FeSnS4. Calculate, oh bloody hell, calculate the relative formula mass of stannate. All right. Now, I'm not going to ask you to do this because, I'm sure you can do it, but I'm going to do it for you because I'm sure you don't know. You don't know some of these numbers. So we do this. We say this: Mr of Cu2 FeSnS4. Okay, Cu2. So it's 2 times 64 plus iron is 56. Tin, I have no idea. You know that? I'm lying here. I'm pretending I know, but I've just looked it up. It's 119. And then we have 4 times 32. Okay, I'm sure you could have all done that. And the answer is 431. So there we go. We got 1 mark at least. Okay. Now, the molecular mass of SnO2 is 151. Calculate the percentage of tin by mass. So what that is the percentage of tin is going to be the mass of tin divided by the total mass of the SnO2. Okay, times 100. Okay, and that equals, well, the mass of tin is 119 divided by 151, that number there, times 100%, and it is 78.8%. Okay, now I can't see anyone. I'm assuming you're with me. Let's go back to you guys. So are we all good? Can I move on? I'm doing this bit on my own a little bit because I'm pretty sure you can do this. Are we good? Anyone want to ask any questions about that? Okay, what's up? You're good. That means you're good. Okay, fine. All right, now moving up. The percentage of tin by mass in Cu2FeSnS4 is 27. Okay, this is the percentage of tin in that compound. Use this information and your answer to be to suggest whether it would be better to extract tin from SnO2 or Cu2FeSnS4. What shall we do, guys? Which shall we extract it from? SnO2 or the other one? Just say the other one. Yeah, exactly. Simple as that. It's easier to extract it from SnO2 because you look at the percentage there because there's more tin. There's more tin in it. All right. So if I have a kilogram of this stuff, and if I have a kilogram of this stuff, the tin I'll get 780 or about 781 grams of tin, but in the other one I'll only get I'll only get 276 grams. All right, so it's much better to get the higher percentage. Tin can be extracted by heating tin 4 oxide with carbon. Carbon monoxide is the other product. Write a chemical equation for the reaction. So here we go. SnO2, that's the tin 4 oxide, reacts with carbon. I'm going to get tin and I'm going to get carbon dioxide. So first of all, that's the equation. All we got to do is balance it. And I'm going to try and balance it. So you need 2 of those. I think it's balanced, isn't it? That's a bit easy. Any questions there? I'm waiting for any questions. I'm checking the answer scheme just in case it isn't balanced. Yeah. Oh, no, I've got it wrong somehow. How did I get it wrong? Sorry. Can you see how I've got that wrong? Anyone? Yeah, exactly. Well done, Annabelle. I messed up, didn't I? So we've got to change this. I totally misread that. So we get carbon monoxide. Now we got to balance it. So let's try and balance it. Well, we've got 2 oxygens here, and we've got only 1 oxygen here. So the only way to change that to 2 oxygens is putting a 2 there. If I put a 2 there, it means I've got to put a 2 there. And now we are done. Any questions? Well done, Annabelle. Good stuff. Let's move up. Whoopsie daisy. The position of tin in the reactivity series is shown. Iron, tin, copper. A student added iron to a solution containing tin ions. The student then separately added tin to a solution of containing copper ions. Complete the ionic equations. Oh, this is good. Okay, so first of all, I'm going to draw the picture. I'm going to put what am I going to put? This is iron. All right, there's a piece of iron, and I'm going to put it in a solution containing tin 2. And then, next one, I'm going to put some tin. Now this is tin into a solution containing copper ions. Okay, so obviously this is looking at displacement reactions. Okay, there you go. So first of all, let's call this number 1 and number 2. Will there be a reaction in number 1? Yes or no? Anyone? Will there be a reaction? Yes or no? Anyone? I'm going to answer because I want to finish the paper if I can. And we've already done half an hour. No one's going to answer? Yeah, there is a displacement reaction. Why? Because iron is more reactive. Fe is more reactive. Will there be a reaction in number 2? Anyone can tell me that? Anyone? Is there going to be a reaction in number 2? No one wants to answer anymore. But yes, there will be. There will be a reaction in number 1. There will be a reaction in number 2 because tin. Oh no, Annabelle. Have I got it wrong? Tin is more reactive, isn't it, than copper? Why are you saying no? Am I wrong? Maybe I've got something wrong. Iron in tin, tin in copper. Is there no reaction? Why did you say there's no reaction? Am I misreading something? Help me, someone. Is there a reaction in number 1? Anyone? I think there's a reaction in both. Lorna has joined. Hello, Lorna. Yeah, there is a reaction. Let's do them individually. Is there a reaction in number 1? Is iron more reactive than tin? Yes. Is there a reaction in number 2? Is tin more reactive than copper? Yes. Okay, guys, don't think because the answer to the first one is up, it doesn't mean the second one is down. All right. In this case, there's a reaction in both. Now, what does it mean then? Well, it means that because the iron, this guy here, is more reactive than the tin, the electrons from the iron are going to go onto the tin. So I'm going to get iron 2 plus, because it's going to lose 2 electrons, and the tin is going to gain 2 electrons. So tin is going to be pushed out of solution. So that's the ionic equation for number 1. We get Fe2 plus Sn. Number 2, the tin is going to push its electrons onto the copper. It's going to push 2 electrons on, so it's going to become Sn2 plus copper, another displacement reaction. Are we all good? Can I move on to the next question? Are we good, guys? Well done. I hope you understand that one. We got a little bit confused there, I think. Let's have a look at this. Okay, whoopsie daisy. Let's copy that. Let's get rid of this. Oh, look at this again. I'm just going to throw it up there. I'll get rid of it later. I'm going to paste this question. All right. Copper nitrate, CuNO3, decomposes when it's heated. The only solid product is copper oxide. There are 2 gaseous products here. Okay. One of the gaseous products is oxygen. Describe a test for oxygen. I'm not even going to insult your intelligence. The test for oxygen is you use a glowing splint, and the result, it relights, doesn't it? Name the other gaseous product. What's the other gaseous product? Anyone? Anyone? Quick. You're decomposing copper nitrate. What's the other gaseous product? Anyone? Quickly. Type quickly. No one? Zara, are you there still? Anyone? What's the other gaseous product? You're decomposing copper nitrate. No one? No one? It's not nitrogen, Eric. It's not nitrogen, Zara. No, it's not NO3. It's nitrogen dioxide. That's right. I'm going to do the equation. Let's do the equation first. It's copper nitrate gets heated. It gets the copper oxide plus nitrogen dioxide plus oxygen. And now we have to balance it. It's 2 of those, 4 of those, and 1 of those. All right. So the name of the other gas, not the formula, the name is nitrogen dioxide. Okay. And this is under thermal decomposition. So guys, you're not very good at this. Look this up, eh? Thermal decomposition. We have to decompose 3 types of compound. We have to decompose hydroxides. We have to decompose carbonates. And we have to decompose nitrates. Okay, you must learn these. I'm not going to do it now, but you've got to learn it. Anyone, what color is nitrogen dioxide? Well done, Zara. It's a brown gas. It's a brown gas. Believe it or not, I don't know if any of you have been to Cape Town, but I was there many, many years ago. And I remember driving up the mountain, and you go through a layer of NO2 gas because of the pollution. And you can literally see a layer of brown gas above Cape Town because the geography of Cape Town is such that it kind of traps the brown gas in. It's crazy. Okay, well done. Let's push on. Oh, we've got like maybe 10 minutes and I want to get the whole paper done. So let's move along here. Okay, iron. What's it talking about iron here? Let's have a look. Okay, iron does not rust when it is completely coated with zinc. When zinc is scratched, the iron still does not rust. Explain why the iron does not rust when it is completely coated with zinc. Anyone want to answer that? Why doesn't the iron rust when it is completely coated with zinc? No. That's not the answer to this bit. No, guys. Not this one. Number 1. Why doesn't the iron does not rust when it is completely coated with zinc? No, Uran, that's not the answer to this one. Catlejo and Lorato, good try. It is not sacrificial protection. Read the question. Why doesn't iron rust when it is completely coated with zinc? You are right, but not for the first part, you're not. Why doesn't iron rust when it's completely coated with zinc? No one? You know what? It's a simple. You're answering a more complicated question. The reason iron doesn't rust is because it does not come into contact with either water or oxygen. It can't come into contact with water or oxygen if it's completely coated. That's how it works. But now, if there's a scratch in the zinc, now you have sacrificial protection. And we've got to answer this nicely. We're going to get 3 marks out of this. So the first thing I would say, I would agree with you all, it's sacrificial protection. I would say that first of all. Okay, and then I would try and explain it. I would say the zinc. Oh God, what's my pen? It's gone all weird. The zinc. Ow! It's all gone scratchy. Hold on. Oh, that's horrible. The zinc is more reactive than iron. That's number 1 point. The zinc is more reactive than iron. So what does the zinc do with its electrons? Anyone? What does zinc do with its electrons? Anyone? I'm going to answer. So, because it's more reactive than the iron and they're stuck together, it gives them up. That's right. The zinc pushes its electrons onto the iron. If I'm pushing electrons onto the iron, can the iron react? If I'm forcing electrons onto the iron, can the iron react? Anyone, quickly? If I'm pushing electrons onto the iron, how does iron react? All metals react by losing electrons. If you push electrons onto the iron, it can't react. Does that make sense? Anyone, please answer. Yes, well done, Annabelle. So the zinc, where are we? The zinc is more reactive. The zinc pushes its electrons onto the iron, preventing it from reacting. However, the zinc loses its electrons and reacts. And that's what we mean by sacrificial. It sacrifices itself for its ion friend. Okay. Any questions there? If not, I'm going to move on. You better answer quickly, guys, because I'm on to the next question. Oh, this one looks awful. This one looks... Oh, no. This is calculation. You know what? I thought we were going to do a calculation earlier, but this is the calculation. All right, here we go. All right. Dilute sulfuric acid. Oh, it's always dilute sulfuric acid. All right, I always use this one. Dilute sulfuric acid. Where are we? There we are. Okay, well done, Annabelle. Dilute sulfuric acid and aqueous potassium hydroxide can be used to make potassium sulfate using the method. In other words, we're going to chuck the acid here. The acid is here. It's going to react with the potassium hydroxide, and we're going to get potassium sulfate and water. Everything looks good. A student titrated 25 cc's of 0.05 molar aqueous potassium hydroxide with dilute sulfuric acid in the presence of an indicator. The volume of dilute sulfuric acid needed to neutralize the aqueous potassium hydroxide was 20 cc's. There's the reaction. Determine the concentration of the sulfuric acid. Woo! All right, I'm going to do it, and you should these things are easy. You shouldn't ever worry about these. I promise you. We're going to get 3 marks, no problem. All right, calculate the number of moles of aqueous potassium hydroxide used. Now, I'm going to do it like I do it. Number of moles is N. I always say that. Number of moles N of potassium hydroxide is equal to CV. Concentration of potassium hydroxide, where is it? There it is. So the concentration of potassium hydroxide is 0.0500 times the volume used, which is 25 cc's. But we can't use centimeters cubed, so we've got to convert that into decimeters cubed. And we do that timesing by 10 to the minus 3. All right. So now I'm going to get my calculator out. Oops, wrong place. There it goes. It's an online calculator. So 0.5 times, you can help me, guys, if you want, 25 exponential minus 3. I get this 0.00125 moles. So the number of moles is 0.00125 moles of potassium hydroxide. Calculate the number of moles of dilute sulfuric acid needed to neutralize this. Now, well, underneath this, I'm going to put 0.00125, and the stoichiometry tells me it's 221. So from potassium hydroxide to sulfuric acid, it's 0.00125 divided by 2. Yeah, because it's 1 to 2. Okay, so it's that number divided by 2. All right, divided by 2. And I get, oh, it's quite small. It's 0.000625. Or if you wanted to be clever, 6.00, horrible. 6.25 times 10 to the minus 4. Okay, calculate the concentration of the sulfuric acid. Well, concentration C of sulfuric acid is equal to the number of moles of sulfuric acid divided by the volume of sulfuric acid. Number of moles of sulfuric acid is this, 0.000625. The volume of sulfuric acid is 20. So we divide it by 20, but it must be in decimeters cubed. And there you go. So it's that. So divide that number by 20, exponential minus 3, and I get 0.03125. I'm going to cheat now, make sure I got that right. I'm normally pretty good at these things, so I'll do okay here, I'm sure. All right, where are we? Yeah, I got it right. Okay. Anyone want to complain or anything there? Please argue with me if you don't agree. Are we all good? Annabelle, you good? Are we all good? I'm moving on. Excellent, well done. All right. It makes you realise how easy it is, doesn't it? Really. All right. Let's do this one. This one looks a bit grotty, but we got. Oh, this is a big question. 18 marks. All right. So, we've done 45 minutes, but we're getting quite close to the end, though. We really are. After the titration has been completed, the conical flask contains an aqueous solution of potassium sulfate and some of the dissolved indicator. Describe how to prepare a pure dry sample of potassium sulfate from new solutions of dilute sulfuric acid and aqueous potassium hydroxide of the same concentration as used in the titration. Bloody hell. How are we going to do this? Okay. Now, does anyone know how we do this? How we approach this? Anyone know? Basically, if you don't know, just anyone want to say something? I'll give you a minute. Anyone want to say anything? No idea. Okay, Eric, it's a good one. All right, let me tell you the problem first of all. Okay, we've got a burette. There's a burette. All right, we've got a conical flask. Okay, and we add this stuff to this stuff, and we get a conical flask here. At neutralization, we have potassium sulfate solution. Okay, and normally all we would do is we'd evaporate the water off, and we'd get potassium sulfate. But unfortunately, in here, there's also indicator. Okay, that's the problem. So let me tell you how to do it. Okay, sit back and relax. All right. Now, what we do is number one, first thing we do is we do the titration. Okay, with an indicator. All right. And find that 20 centimeters cubed of acid neutralize the potassium hydroxide. That's what we did in the last one. So is everyone happy with that first step? All we're going to do is all we're going to do is exactly what we've done. Anyone scared so far? Are we all good? All right. So we do the titration with an indicator. Now, and this is the clever bit, number 2, all right? The next time we do it, we do the titration, okay, without the indicator. Okay. How much do I add though? How much sulfuric acid shall I add? Anyone? Well done, Achika. We do it without, and we trust our first result, and we add 20 centimeters cubed of sulfuric acid. So now we have a conical flask containing potassium sulfate in, and there's no indicator. Isn't that cool? All right, I think it's cool anyway, but I'm a bit nerdy, I'm afraid. All right, so there we go. And now what do we do now? Okay, next thing we do is we take this water here, we'll take the solution here, and we evaporate. Oh, my pen's gone weird again. Evaporate until the solution is saturated. So we evaporate most of the water off, but we don't evaporate all of the water off. Okay? All right, we evaporate. How do we evaporate? We heat. I should have said heat. Heat to evaporate until the solution is saturated. And now number four, what we do once we've got a saturated solution, we leave to crystallize. Okay, and we get lovely crystals. All right. And now the next thing we do, number 5, we've got lovely crystals. All right. Next thing, we wash them. We wash the crystals with. Now, we can't wash them with water because if we wash them with water, they'll evaporate. So, what am I talking about? If we wash them with water, they'll dissolve. So, we wash the crystals with an organic solvent, something like ethanol. And then, number 6, we dry the crystals. Dry crystals with filter paper. Ugh. Are we all good there? Are we all good? Did we get that? Why would it still be 20 if it was that when there was an indicator won't change the results? No, the only thing the indicator does is it tells you how much acid you need to add. Okay? If you know, the indicator is going to change when I have added 20, and then you do the sneaky thing, you do it again without the indicator, and you add 20 again. Does that make sense? Yeah? Now, ladies and gentlemen, this is a big thing. All right, now I'm going to put a thing around here. This thing, now my English is awful, as you can see, okay? But I tell you, if you're serious about doing your chemistry, learn this, okay? How to make it. All right, this is a titration method of making salts. Now, if you love chemistry, well, you probably know it already. If you don't love chemistry, just learn it. Write it down 3 times. And yeah, I would do it in bullet points myself, Yaran. I really would. You know what? When I'm marking student stuff, um, the ones that put it in bullet points generally do better because they do it in order. I would always use bullet points. If I look at the mark scheme is in bullet points as well. But you don't have to do bullet points. Thing is, if you don't do bullet points, though, you guys tend to just waffle on a bit, don't you? Which is it goes on and on and on. All right, like I'm doing now. All right, potassium hydrogen sulfate is an acid salt. It dissolves in water to produce an aqueous solution X containing K, H plus, and SO4 2 minus. Describe what you would see when the following experiments are done. What would happen if we put magnesium ribbon into an excess of solution X? What would I see? Magnesium ribbon. Anyone? Into a solution of X. Anyone? I don't know why it's worth 2 marks. I can only think of 1 mark. Anyone want to tell me what I see? Okay, all right. Anyone? What would I see if I put magnesium ribbon? Yeah, and what? Right now, you're very right, all of you. First thing I would see is effervescence. Why am I seeing effervescence? Even though it doesn't want us to explain it, why do I see effervescence? Anyone want to answer that quickly? Don't put. Why have you got question marks after your effervescences? All right. Yeah, exactly. So, yes, it's gas production, but the magnesium is reacting with what ion is the magnesium reacting with? Look at the ions in solution, and what ions is it reacting with? Exactly, Catlaho. It's reacting with the H plus. And what do we call an H plus ion in solution? What's an H plus ion in solution? Exactly, Layla. An H plus ion in solution is acidic. So what you're doing is you're adding magnesium to an acid. Simple as that. Yeah. Now that's one observation. What's the second observation? That will get you 1 mark. What will get you the second mark? I think this is a bit of a cheap mark, but they often do this. What's the second mark there? Well done, well done. Yeah, the ribbon dissolves. Well done, you're better than me. The ribbon dissolves. Gets smaller. A flame test on the X. What would I see? Oh, this is going to test you. What flame test? I can see one colour there. Anyone see that? What flame colour would I see if I tested X? Colour, colour, colour. Well done, Catlo. Nice one. How do you spell lilac? You're better than me. An aqueous solution containing barium ions is added to X. What ion is barium going to react with there? What does barium test for? Barium ions. We do this in lab all the time. We add barium ions, and what are we testing for? You've all forgotten, haven't you? We use barium nitrate or barium chloride. It's a test for what? Oh, guys, really? Oh, all right. I'm going to slowly get a black pen. No one? Right, it's going to use a blue pen. Okay, barium ions, where are they? Barium ions are a test for sulfate ions. And if sulfate ions are present, we get barium sulfate. It doesn't want you to say that, but barium sulfate would appear as a white precipitate. I hope you're good. It'll be good there. All right. No one's saying anything, so I guess you're good. Okay. Dilute sulfuric acid reacts with bases, metals, and carbonates. Write a chemical equation for the reaction of dilute sulfuric acid with the following: magnesium hydroxide. Anyone want to tell me what I'm going to get? Magnesium hydroxide. Yes, of course you can, Annabelle. No worries. Zinc and sodium carbonate. All right. So I'm going to add this to sulfuric acid. I'm going to add this to sulfuric acid. And I'm going to add this to sulfuric acid. Okay. What type of reaction is the first one? The first one is an acid plus base. The second one is an acid plus metal. And the third one is an acid plus carbonate. What am I going to get then? Acid plus base. I'm going to get water and a salt. And the salt is going to be magnesium sulfate. Is that balanced? No, I need to put a 2 there. Now it's balanced. Zinc plus sulfuric acid. I'm going to get zinc sulfate and hydrogen. That's balanced already because it's an acid plus metal. And the last one, the most complicated one, I guess, I'm going to get sodium sulfate, which is Na2SO4, plus carbon dioxide plus water. And that's balanced. Do we all understand that? That one, you just got to learn a bit of inorganic chemistry. It's not hard. You got to know how acids react with hydroxides, metals, and carbonates. All right. Oh, gosh, right. Well, we're nearly time up. Oh, we didn't get to the organic. Oh, what a shame. Right, I'm going to quit question 5. And then I'm going to do, oh gosh, what am I going to do? Then I'm going to jump 2 questions. Am I going to jump a question? Maybe I'm not actually. I'm going to jump 1 question, okay? All right, one of them's a bit weird though, I must admit. We're going to jump question 5. To be honest with you, we're quite close to finishing, and I've been talking a lot, haven't I? In an exam, you would have easily finished this. All right, but let's try and do this one, and then we'll call it a day. Ethanol can be... This is quite a horrible question, by the way, because it's worth 6 marks, and look at that, a lot of writing. Ethanol can be manufactured by fermentation and by hydration. Describe 2 processes of ethanol manufacture. In each case, identify the reactants, give the reaction conditions, write a chemical equation. Okay, how are you going to make ethanol with fermentation? Now, what we need is glue. Oh, what's going on there? We need We need glucose solution. Okay, so we need glucose and water, and we need yeast. Okay, and the temperature for fermentation is about 30, I don't know, 36, something like that. So we've got the reagents, yeah, we've got the conditions, right? Chemical equation, okay. So it is this, it is C6H12O6 plus, no, it's not plus anything, is it? This aqueous gives me 2 ethanol, C2H5OH, aqueous, plus 2 carbon dioxide gases. That's it. 3 marks. Easy. All right. Next one. Hydration. What do we need for hydration? Well, we need ethene. All right. We need steam. Okay. The conditions. All right. The conditions for hydration. All right. Does anyone remember what the conditions for hydration are while I'm doing this? Anyone know the conditions for hydration? We're adding steam to ethene. All right. Okay. Anyone know? Steam to ethene. Steam to ethene. Oh, I think I can't see you. Right. Anyone know steam to ethene? Well, oh God, you're better than me, guys. By a long way. I don't think I'd have known that. All right, yeah, you're better than me. I'm hopeless at these things. All right, so steam to ethene. That's easy, I guess. The catalyst is phosphoric acid. I remember this. Phosphoric acid is H3PO4. Okay, and it's normally used in the solid form. Okay, now I would have thought it's about 200 degrees C, but I'm cheating. I'm looking at the answer. I would have got a mark for phosphoric acid, but according to this, it says 300. So remember that. And also it's 60 atmospheres. Okay, it's quite high pressure. Now, you didn't need all 3 of these. You only needed 1 of these. One needed only for the mark. Okay, this one you needed both, steam and ethene. This last one you needed just one. Okay, so try and remember one. And what's the reaction? Well, it's ethene plus water gives me ethanol, C2H5OH. All right. Give 2 advantages. Don't worry, I'm sure you're all tired, guys. We're nearly done, eh? Well done, Lorna. Well done. It's phosphoric acid. Give 2 advantages of ethanol manufactured by fermentation compared to hydration. Anyone want to say what they think the answer is there? Why is that? All right. It's obviously the things we talk about these days, isn't it? So carbohydrates are renewable. Okay, ethene is not. We can grow carbohydrates, but we can't grow any more ethene. Okay, fossil fuels, these guys are non-renewable. Okay, so if you can not use them, the better. Okay, another advantage is for the carbohydrates. Look at the temperature. For fermentation, it's low, and for this, it's much higher. So these can be done at lower temperatures. Fermentation is a lot lower temperatures. All right, and that means you save energy. All right, it's two major uses of ethanol. What are 2 major uses? I think we all know one. Yeah, it's cheaper. Yeah, 2 major uses of ethanol. Anyone? Let's have a look. I'm cheating here because I want to rush a little bit. Okay, they're the 2 I would have picked. We use ethanol for a fuel, and it's used as a solvent. And you could have also said, yeah, it's a solvent. It's a big solvent. If you've ever used perfume, the solvent you would have used is ethanol. And it's also a constituent, and it's not constituent of wine and beer, isn't it? We do use it for that. There's no point pretending we don't. We do. All right, so that's that. Nearly done, guys. Oh, shame. I don't know why we're a little bit slow today. I think it was probably me. All right, we're on the last page. Oh gosh, this looks awful. Why is this the last page? Oh no, it's not bad. Last page, And you've done very, very well. Structures of some polymers are shown. Oh my God. Let's have a look at this. Woo, this looks tricky. Okay. Don't worry, you are. We're going to sort it out. Answer the following questions about the polymers. Okay. Now, the first thing it's asking for an addition polymer. Can any of you see the addition polymer there? A, B, C, or D? Eric thinks it's B. No, that's not an addition polymer, I'm afraid. Okay, it's very simple, guys. There are two types of polymers, eh? Yes, it is E, Ketlo. Well done. We have addition, okay, and condensation. Condensation. Addition is always carbon, 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 carbon. All right. Condensation has these funny things. It has an ester link or it has an amide link. Okay. But addition is carbon, 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 carbon. And the only one with carbon, 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 carbon is E. So that's E there. That's how you remember it. That's how I remember it. Which one is a protein? Anyone see the protein? Protein. Protein, D. Yeah, I'd go with that, Lorata. Well done. D is the protein. Which one is a polyester made from only one monomer? Well done, Lorna. D is the protein. Which one is a polyester made from one monomer? Yes, you're right. This group here is the ester group. This group is the ester group. So both of these are polyesters, both of them. But you see, this one has different units and this one has the same unit. So if it's made from one monomer, the answer is B. Which one is terylene? Terylene. Which one's terylene? Yeah, it's C. Well done, Tiso. And which one is a complex carbohydrate? Which one's the complex carbohydrate? Oh, we don't know. A, that's right. It's starch, isn't it? Okay. This page is a good page. All right. This is a good page to learn from, seriously. All right. That's good revision, that page. Now, before you go, well done, first of all. I'm going to turn off the video. Here we go.